So in this video, we're going to do lots of factoring. It's going to be an important skill to have pretty much in all grades of high school, plus calculus right at the end. And so when we deal with factoring, we're just taking these terms that look like these types of problems and breaking them down into smaller elements. So in a problem like the first one, I basically look at it and I say 9 and 12 can both have a factor of 3 in them. So that's something I can take out of both. And then what about the x's? Well, we can take an x off both of them because they both share an x. So I remove the 3x and put it out in front. And then that leaves me with 3x because 3x times 3x is 9x squared. And then if we take a 3x off negative 12x, we just are left with negative 4. And we don't need to go any further in this case because when they say factor, they just want to put it in smaller, simpler terms like this, not actually solve for the roots, which would be a step further past this. In the case of the next problem here, the only difference is that now we have a constant term out in the back there. So instead of having 2 terms, we have 3 terms. And the way to tackle these types of problems is I like to draw an x off to the side because I say in these types of problems, we have to do what will multiply to make the coefficient out here, so 1, and the end product, so 1 times 15, what will make 15, but then add to make negative 8, or add to make the middle term. In this case, we can say that those two elements are negative 3 and negative 5, because when we add negative 3 and negative 5, we get negative 8, and when we multiply them together, we get 15. So then when we go back to our problem, we say that x squared, we're going to write out those factors, plus 15, and then now we want to treat them like 2 separate terms. So in this case, you want to treat these 2 together, and then you want to treat these 2 together. And someone might ask, they say, well, does it matter what order we put the 3 and the 5? No, because you'll get the same result in the end. So whether you put the 5 here or the 3 here, it will be the exact same result, but you just always want to be thinking about them as we want to deal with them 2 terms independently like this. So then once we have it like this, we're going to repeat the same type of process that we did in problem 1 up here. We're going to say that what can we take out of the x squared minus 3x? Well, we can take out an x. So let's write that x. We're going to be left with an x minus 3. And then what about the other side? The other side has a negative 5x plus 15. Well, we can take a negative 5 off that, which will leave us in brackets x. And then since it's a positive, we're going to have to make that a negative 3 out here. And so now this is a great sign because when I look at this, if we have the same term in both our factored brackets like this, then we know that we've done the right steps. And then at this point, we're just taking these 2 terms, the ones that are factored out from our brackets, and putting them together. And then we're only putting one of these terms. And so what I mean by that is that we're going to now write it as x minus 5 in brackets is the one term, and then multiplied by x minus 3 is equal to 0. We always set it equal to 0. You can do that along the way or at the beginning, but especially at the end, that's going to be important because basically you're solving for roots. But in this case, we're just getting to the factored stage. Okay, so now we're going to tackle 4 more examples here. So when we look at 2a here, we're saying, okay, well, the only difference from our last problem, which had a singular term or a 1 in front of our x, like it does here, now we have a 2 in front of our x. So how is that going to change our answer? Well, we'll see how that looks. So like we said last time, we're going to draw our x. And so we need a term that will multiply to make 2 times 5, which is 10. And then add to make the middle term, which is 11. So in this case, what are those 2 terms? Well, we say if 10 plus 1 is equal to 11, so we'll put 1 and 10 as our guess. If 1 plus 10 equals 11 and 1 times 10 equals 10, then boom, we have our factors. So now, like last time, we're going to rewrite it out, but with the factors this time. So we'll do plus x plus 10x plus 5 on the end. And then like we did before, we want to say that let's group these 2 terms together, and let's group these 2 terms together, and let's factor out what we can from both of those. So in the first case, we can only factor out a common x. So we're going to write it as x, 2x plus 1. And then what about this next one? It looks like we can only factor out, I I think a 5 from both of them. So we're going to do plus 5 x, 2x, sorry, plus 1. Okay, so that's looking good. We have the exact same thing in both brackets. So we're going to look at them, remember, as group these two together and then group one of these, and that becomes our factors. So we say that x plus 5, all in brackets, times 2x plus 1 is equal to 0. We have the same scenario here. We have a non-1 coefficient, and we have a regular trinomial. So in this case, let's draw our x again. So we're going to say that we have our x. What multiplies to make 4 times 25? Well, that's 100. And then what adds to make the middle term, which is 20. In this case, I would say 10 and 10, because 10 times 10 will give us 100, but 10 plus 10 will give us 20. So let's write those two terms in now. So we have 4z squared plus 10z plus 10z, because they're both 10s, plus 25. Okay, so now we want to treat them as our two separate terms. So we're going to have our first term here, our second term here, and then now let's factor what we can from both of them. So in this first one, it looks like we can take a 2z out, because a 2 goes into 4 and a 2 goes into 10, and they both have z's, so we'll take that out, plus 5 left over. And then what about the second term? It looks like we can take a 5 out, I believe. Yes, plus 5, 2z plus 5. And then like we did before, we want to say that if we have this term and this term, we can group those together because our interior brackets are the same thing. And then we just want to take one of these. So in this case, we say that if we group the two green terms together, we have 2z plus 5. And if we put one of those blue terms together, we say 2z plus 5 is equal to 0. But then there's something unique we should notice about this problem that's a little different than the other two. Well, if they're the same term, we got the exact same factors from both of them, let's group them together. If we have two of the exact same term, we can actually just say it's squared. 2z plus 5 squared is equal to 0. All right, in our last two problems, we have 3p squared minus 8p plus 4. We're going to do the exact same steps as we did before. So we're going to draw our x. We're going to say what multiplies to make 3 times 4, which is 12, and adds to make the middle. In this case, we would say, okay, well, those are -2 and -6, because -2 minus 6 is -8, but -2 times -6 is 12, because a negative equals a positive. So in this case, we're going to rewrite out our terms with our factor, minus 6p plus 4. Do what we did before, where we're going to treat them as two separate terms. So we're going to have our one term there, second one here. Okay, and so what in the first one can we do? We can take out a common p, it looks like. So we're going to take out a p from there, and that will leave us with 3p minus 2. And then what can we take out of this one? Well, it looks like a 2 from 6 and 4. So we're going to say minus 2. And if we pull a 2 off of 6, that's going to leave us with 3p. And if we take a 2 off of 4, that's going to give us a, well, since it's a positive term, we're going to have to make this a negative as well, like we did in the previous problem. And then so what we're going to do is at this point, we have common brackets there. So we have a p and a 2. And we have same terms in, so we're going to only have one of those. And so at this point, we're just going to say that our first bracket is p minus 2, and our second bracket is 3p minus 2, and then set it to equal to 0. All right, and then our last problem actually brings up a really unique scenario. So what we call these problems is a difference of squares. And so what we mean by that is that we can have perfect squares on both of our terms. So for this one, we can actually say that this term breaks down into 4x times 4x, because 4 times 4 equals 16, and x times x equals x squared, And then when you combine them together, that's going to give you 4x times 4x, which is 16x squared. And then our other one here, our 81, well, 81 is actually just 9 times 9, because 9 times 9 equals 81. So what does that give us for our problem? Well, that means that when we have a difference of squares, we're going to treat it as one of these terms plus the 9, so plus the factor from the other one. But then our second term becomes 4x minus the 9 is equal to 0. Okay, finally, I just wanted to put some clarity on what difference of squares is and put it in its general form so that you guys know. So when we have a problem like our last one where we have that 16x squared minus 81, or anything that's a square form, even like an x squared minus a 25, anything that's a difference of squares and it's identified as a difference of squares, we say that its general form looks like this. It's a squared minus b squared is equal to a plus b times a minus b. And so this should put some clarity on our problem that we just worked on, because we said if 16x squared is equivalent to a squared in this case, and b squared is equal to 81, then when we put it in our final form, we said, okay, well, if a singular a was 4x, or if this can be broken down into 4x times 4x, and this one, 81, can be broken down into 9 times 9, then it should make sense that a singular a is equal to 4x, and a singular b equals 9. So now we just have to fill in the gap of 4x plus 9, and then same thing over here. So we just need to remember that this a squared minus b squared is our general form there.